Hello everyone, my name is Neha and this is the 19th lecture on Introduction to Microcontrollers. In this lecture, we're going to see a project named Temperature Indicator, and we will learn about how to write a program for analog to digital conversion, which we'll be using for this particular project. So let's get started. So the goal for this project is to use the development board. You will be using PIC16F 18875 high curiosity development board. And if you're using higher version, then you can use that. And maybe in the higher version, some of the instruction set might be different, but most of the code is going to remain the same. So you'll be using the development board, and you're going to write the temperature indicator program with the following specifications. So the first performance specification is to measure the temperature with the MCP9701 sensor and use the PIC analog to digital converter to read the temperature. And next specification is compare temperature measurement with a reference value of 75 degree Fahrenheit. And third is use LEDs to indicate the status of temperature: red for high, blue for low, and green for on target. And note the LEDs can be of the same color. So you will be using MCP9701 sensor, and that sensor has been shown here. So this is your MCP9701 sensor, and you'll be converting analog to digital. You'll have to do analog to digital conversion, because this sensor will receive the temperature as your non-electrical quantity, and you want to convert that non-electrical quantity into the electrical quantity. Okay, so and then electrical quantity must be converted into a digital signal, and which will go into the microcontroller. And you are going to compare the temperature measurement with a reference value of 75 degree Fahrenheit. So 75 degree Fahrenheit is going to be your reference temperature. And you have to measure the temperature up. You will have three different temperatures. One is going to be your target, and other two is either going to be high or low. And with respect to the reference temperature, you are going to check whether your temperature is higher than the reference value or lower. So you will and these three LEDs, as it says, use three LEDs to indicate the status of the temperature. So these three LEDs are going to indicate whether your temperature is high or whether your temperature is low, or you are at a target temperature, which is the 75 degree Fahrenheit. All right. So these status indication has been shown here with these LEDs. LED 1, 2, 3. LED 1 is for high temperature. LED 2 is for target temperature or normal temperature. LED 3 is for low temperature. And you can use different color LEDs to indicate the result. Red one you can use for indicating the higher temperature. Green one you can use for normal temperature or target temperature, and the blue one you can use for low temperature. And then this is your microcontroller, and then some capacitors are used, and this is the resistor, and here these are some of the resistor connected to the LEDs to limit the current. So your circuit doesn't have to be exactly like this. You can be more creative with the circuit, and if you want to add a buzzer or something like that, you can do that. So yeah, I'll just leave it on you to be more creative with the circuits, but here is the sample circuit I've shown here, which you can refer to. This is the supply list. You'll be using breadboard, MCP9701 sensor. You'll be using microprocessor, this particular microprocessor. Curiosity HPC development board. So this is the part of this development board. And then USB to micro USB cable. You'll be using three LEDs and 100 ohm resistor, jumper wires, computer with MPLAB of this version. So these are some of the basic supplies, but again, as I told you, that you can be more creative. You can use buzzer or something else to show the status, change in status of the temperature. And this slide talks about the breadboard circuit for the simple temperature indicator circuit, and this is another example of a temperature sensor breadboard circuit. You can see these are the three different LEDs which are used: low, target, and high LED, which represent different temperature status. And then this is your sensor MCP 9701 has been used, and these are some of the jumper wires, and you can see how they are connected to the microcontroller, this development board. Okay, so this is just an example for this temperature indicator project. Now I'm going to move on to the this table, which has been taken from the data sheet of MCP 9701 sensor. So if you see the data sheet for of this sensor, you will find this sensor output table. And what we are trying to see from this table is to check the temperature coefficient and offset voltage. So for 75 degree Fahrenheit, the temperature coefficient is more precisely is 19.5 millivolts. You can see here, this is the TC. And also there is an offset which is there, is 400 millivolts. So we will be converting the temperature into the voltage. So we'll be converting three temperatures into the voltages: one for reference temperature, second for higher temperature, and the third for lower temperature. So all these three different temperatures will be converted into the voltage, and that we are going to see in the next slide. So there are some formulas which you use to convert into the reference voltage. The first thing what we are going to do is to convert the temperature from degree Fahrenheit into the Celsius. Okay, so to do that, we'll use this formula. This is our reference temperature, 75 degree Fahrenheit minus 32 divided by 1.8, and if you use this formula, this will give you 23.89 degrees centigrade. And so this is your temperature in centigrade, or you can say Celsius. Both are the same thing. And reference voltage can be determined by using this formula, where you multiply the temperature you got in Celsius with the temperature coefficient voltage. So we saw that in the previous slide. So this is the temperature coefficient in millivolts per degree Celsius. So we'll multiply this with this temperature, reference temperature, and we will add the offset of 0.4. We know that we saw it already in this slide, that this is 400 millivolts. So we are going to add that, and whatever the voltage we will get is going to be our reference voltage. Now second is the lower temperature. So for lower temperature, we are going to do the same thing. So let's say the temperature is lower range we are putting is 74 degree Fahrenheit. 75 degree Fahrenheit was our reference, so less than that is our lower temperature. Converting it into the Celsius, so using the same formula, so by applying this formula, we got 23.33 degrees Celsius. And then using this degree Celsius and putting into the formula to get the voltage, we have put this value. This is the temperature coefficient voltage we got here, and then offset, and then so after calculation we got 0.856 volts. This is our lower voltage, and then the same we will do for higher temperature. So the higher temperature we have set it at 76 degree Fahrenheit. So converting into Celsius, we got 24.44, and the formula used is same. Higher temperature, higher voltage, you take this degree Celsius here and then multiply with this value plus offset, it's going to give 0.877 volts. So you can see that this voltage is higher than this, and this lower temperature voltage is less than the reference voltage. So we got three different voltages. Now the next task is to convert these voltages into the bit pattern. So how we are going to do that, we'll see in the next slide. So pick microcontroller voltage per bit. So we know that in the microcontroller which we are using can support 10-bit result when you do the analog to digital conversion at 5 volts. So 5 volts divided by 2 to the power 10, because 10 is your 10 bits, that's why you have 2 to the power 10. That will give you 1024. So if you divide them, you'll get this much volts per bits. And then these volts per bits we are going to divide from all the three different temperature voltages we got. So you know, we got this one for the reference voltage, reference temperature voltage. So dividing it with this, we got 177.66. And if you convert it into bit pattern, you remember I showed you in the last lecture how to convert from value like this into the bit pattern. So you'll apply the same method and you'll get this value. The same we will do it for the lower temperature. Divide this volts per bits by this and we will get this value, and the bit pattern for this one is here it is. And then for same for higher temperature, this voltage divided by volts per bits pattern, and then you got this value, and then converting it, and we'll get this bit pattern. So you see all these bit pattern, how they are different, a little bit different from each other. And then if you have any confusion, then I would say like pause the video right now and try to convert these values by yourself and see if the result matches with this one or not. Now you know the bit pattern, so the next step would be to start doing the analog to digital conversion, writing the code for that. So we're going to see that in the next slide. So A to D conversion operation, initialization. We will first initialize port A. First we set trace A for the appropriate input and output state. So main program code, and then above this main program code you will have some constant registers which you'll be using for your particular program. So starting with this, so you'll start with bank cell port A. You'll clear the port A, and then you will select bank cell N cell A, and you'll clear the N cell A. And once you do that, it means you're making port A as digital. Okay, and then after doing that, you will select bank cell trace A, clearing F trace A. If you clear or you provide 000 hexadecimal to trace A, that means you're making port A as output, and output digital. Okay, so this is the initial starting code. You can make some changes here if you want. And then comes the critical part, which is the channel selection. And you will be using ADPCH register. So you will use first bank select ADPCH, because this particular register, it lies in I think bank 1. So you can check that again from the data sheet which bank it is lie on. So you'll bank cell ADPCH, and then you will be moving this literal number which is 00010010. You might be thinking, why are we moving this literal number into the ADPCH register? So this, you can see this has been taken from the data sheet, and I also showed you in the last lecture how this particular register looks like on the data sheet. What are the different bits it has, and these are the different bit patterns. And as I said earlier, that starting from here, this A and A starting from 0 to 7 is for port A. A and B is from 0 to port for port B from 0 to 7. 8-bit, and then A and C. C stands for your port C. So from 0 to 7. So we, in our example, we are taking RC2 bit. So RC is from port C, and in port C again it has 8. It is a 8-bit register starting from ANC0 to AN7. So we are picking RC2. Okay, so if corresponding to RC2, the bit pattern we have is 010010. So that's the reason why we have used here. So in case if you're using any other register bit, for example, let's say if you're using A and A, which is RA4, then you might have to use this one. 000100. And in case if you're using a register from port B, let's say you're using A and B2, then your bit pattern is going to be 001010, and you'll be using that here. So our case, we are using RC2 as our analog channel, and that's why we have used this bit pattern. So this particular register, it is used to select the channel, and we have used this particular bit as our analog channel. So now the next step is to bank cell tris C. We are using tris C. So far we have used tris A, and now we are using this another one, tris C. And what we are going to do is to set RC2 as our input. Okay, so how to provide it as an input? By using this BSF tris C comma 2. So this 2 is, it will tell like on which bit you want to set it up, and we want to set it up at second bit. That's why we have used BSF. And if you want to use the longer version of the method, you can use something like this. You can provide some literal number and then move W to F, where you can put tris C. So either you can use this or use that, or you can use any other instruction set to tell your microcontroller that you want to set RC2 as your input. All right, so after doing that, you will select bank cell N cell C. So you remember I told you like there are so many N cells, N cell A, B, and C. And in the last slide, we use N cell A, which has been used to define port A as digital, and tris A as used as digital output, defining output. So we use here N cell A, and we are using here N cell C. And we are setting N cell, the second bit in the N cell C, as we are setting it up. So when you set it up as 1, then that means you want to make it as an analog. So we are making RC2 as our analog input. So you get my point here. We have defined it as an input, and here using this N cell, we are defining it as analog. And in case if we want to define it as digital, then we will be clearing it up. Like we will, instead of BSF, we may use like BCF, bit clear F, and then that will behave as your digital input. So again, for this particular case, we are using RC2 as analog input. So making it as analog, N cell C, setting the bit, second bit as 1, and then RC2 to input using tris C. So that's how you select the channel and you write this code. And then the remaining tasks are to set the ADCON1 and ADCON0 register as appropriate. So you have you'll be selecting ADCON1, and you will move this particular bit pattern into ADCON1, and this will configure ADC. And I want you to look it up why we are making this all these ones. For that you have to see ADCON1 register, and you will see these 3 bits has some purpose. So this is your task to figure it out why we are making this one, because the data sheet tells everything. For this, if you look it up for this particular register, it will tell you why we are making this one. So that is something I want you to figure out by your own. And then same with ADCON, you select the ADCON, ADC, ADCON 0, and then you will transfer this data. So here, let me tell you, for this one, when you put here 1, and if you look it up, the data sheet for ADCON 0, you will see at this particular point, you have AD FRMO, which is used. If you set that up, that means you want to put the result in the right justified form. Okay, again, as I said before, please look up these two register in the data sheet and just match it up why I'm putting these bit values and why I'm putting bit values for this one as well. So I just gave you the hint. So this one is for right justified, and this one also has a purpose. So look it up. I've already written actually here, turn on the ADC. So this one is for turn on the analog to digital conversion if you set it up, and it will stop if you put it here 0. And this one is for making it right justified, and if you put 0, that means it will put the result in a left justified form. Okay, now moving this literal number into the ADCON 0 register and calling the delay. And then you have to write the code for delay, and you already have it by now. And then BSF ADCON 0, and in that this ADG 0, I explained it in the last lecture that you have to set this ADGO. If you set this up in ADCON 0, then it will do the conversion. It will start doing the conversion, A to D conversion, and then you will do the bit test F skip if clear. If this is clear, then you're going to skip this step and you'll go to this reference temperature check, where this reference underscore temperature underscore check is the label, and you will have some code for this particular label, so it will go to this label. You understand? So you'll put your code under this label. You don't have to use this exact label. You can name it anything else. For example, just target temperature or reference temperature, whatever the label you want to give, you can. So bit test F, skip if it is clear. If it is clear, so skip it. Skip the step and go to this step. Okay. And if it is not clear, then go to $-1 instruction, where $-1 means going back to this this step. Okay, so if it is not clear, it will go to $-1, and this instruction set basically takes you back to this this line, and it will test it again. Okay. So this is the basic initial code for temperature indicator project, and then the next step would be for you to write the code for target temperature or reference temperature check, whatever the label you want to name. You have to write the code for that, and you'll have to write the code for when the temperature is above the reference temperature and when the temperature is lower than the reference temperature. So for that one, you have to write the main code, and then most of the code is already here. How to initialize the analog to digital conversion is here, so you can use this code starting from here. You can use all of these codes for your program. So this is the end of the lecture. Thank you so much for watching.